Welcome to EPG Pachala. I am Dr. Venusatini from the Department of Philosophy, University of Hyderabad. This is Logic 1. The module on which I'll be talking today is Derived Rules and Replacement Rule in Axiomatic System for Sentential Logic. The module is written by Dr. Smita Sirkar. Before we go into the main module, let us quickly review the earlier module because this is a build-up, a continuation of module number 7. So, what is an axiomatic system? In the module that we have seen before, an axiomatic system is comprised of certain basic truths which are called axioms. And with the help of these axioms, we are able to see its connections with other truths in the logical system. How do you find this connection? With the help of some rules. Those are called replacement rules or rules of uniform substitution. So with the help of these rules, we find connection of true sentences. So let us quickly see what are some of those important axioms for our axiomatic system. Axiom 1. Either P or P implies P. This is a tautology. Axiom number 2. If Q, then P or Q. This is axiom of addition. Axiom number 3, which is permutation. It says if either P or Q, then Q or P. Axiom number 4. If either P or Q or R, then Q or P or R. This is axiom of association. And the last axiom, the fifth axiom, is called summation, and it reads like this. If Q implies R, then if P or Q, then P or R. We have just seen the axioms, and this will constitute what is so-called axiomatic system for sentential logic. But as mentioned, we will also need some rules which will help us to derive theses or so-called theorems. Let us look at these two rules. Rule 1 is called Detachment Rule, or normally it is called modus ponens rule. It is like this. If A implies B is a thesis and A is also a thesis, then we can infer that B is also a thesis. I repeat, if A implies B is a thesis and A is also shown to be a thesis, then we can infer that B is also a thesis. Rule number 2 is called rule of uniform substitution. It says that if we have a complex sentence A and it is a thesis and one of its part is there, we call it B, then we can uniformly substitute its part B by C, and the resultant new formula that we get, which we may call D, is also a thesis. So these are two rules that we have. Now with the application of these rules and given the axioms, we can derive these important theorems. I will review a few important theorems for us. Let us look at the theorems. Theorem 1. P implies negation P implies not P. Simply put, if a sentence negates itself, then it is false. Theorem 2. Q implies P implies Q. That is, if a sentence, let us say Q, is true, then it is implied by any sentence, true or false, which we may here call it P. Theorem number 3. If P implies not Q, then Q implies not P. In other words, if P is the antecedent and we get negation Q, that is denying Q, then affirmation of Q will lead to or will result in negation of P itself. Theorem number 4. If P implies Q implies R, then Q implies P implies R. In other words, if for a truth of a sentence R, we have two conditions like P and Q, then we can also change the position of the conditions. So PQ has become Q implies P implies R, and it doesn't affect the truth of the sentence. Theorem number 5. If Q implies R, then if P implies Q, then P implies R. Normally this is the basis from where we get this rule of hypothetical syllogism. That is, if Q implies R and Q itself is implied by another sentence P, then P also implies R. Now we have just reviewed or recapitulated module number 7. We have seen what are axioms and what are the rules of axioms, rules of inference, and then we have also seen some important theorems which can be derived from the given axioms. From here we get some idea that if we get more theorems, that means we can also use these theorems for proving or deriving more theses or so-called theorems. So in other words, we can have more and more rules if more and more theorems are proved, because now theorems are functioning more like an axiom, where we have seen in the early modules that axioms can be brought in anywhere as part of the proof. So also if proof can be given for those theorems, then we can use theorems themselves as part of the proof. This very idea is called derived rules. So in other words, derived rules help us to shorten the length of the proof. The second point is that it is redundant. Redundant in the sense that these rules are not new, or that even without these rules we can derive some theorems, or more importantly, a full proof of this theorem, these derived rules can be provided. And in this module we will be mainly looking at that, how we can provide a full-blown proof for these theorems. And theorems will be the proof for these theorems, which are called derived rules, will be given in meta proof. And we will go on to see how these derived rules can be used to shorten the length of a proof. Now we will give a new name to these derived rules. SYLL is the short form of derived rules. So we have conveniently given the name SILL to these derived rules. One of the examples is these. If alpha implies beta and beta implies gamma, then we can infer the conclusion alpha implies gamma. Now what we will do is this. We will take one theorem which we have already discussed in module number 7, and then we will give a full-blown proof of this theorem. In other words, how this theorem can be derived from those axioms. Next, after giving a proof of this theorem, we will see how we can use this theorem or so-called derived rules to shorten the length of other proofs. Now let us look at theorem number 8, the one we have seen in the earlier module, P implies P. This is theorem number 8. As suggested above, now we will give a full-blown proof of this, and after that we will shorten the proof. Now let us see how this proof can be shortened. So in order to prove this, we will begin by appealing to theorem number 5, which says that if Q implies R, then if P implies Q, then P implies R. We will use this theorem to get the next step, how by applying the rule of substitution. In other words, every occurrence of Q now will be substituted by P or P, and every occurrence of R by P. So this is what we get after substitution. P or P implies P. The whole thing implies P or P. Together implies P implies P. Now the next step is to introduce axiom number 1. Keep in mind that we can introduce axioms and already proved theorem as part of our derivation anytime. So here we have introduced axiom number 1, that is, if P or P, then P. So the next step is we can appeal to modus ponens rule or detachment. See, P or P implies P is the antecedent of step number 2. So if we apply this rule of detachment, then we can get the consequent part, that is, if P implies P or P, then P implies P. So we get the fourth step. Now we can introduce another theorem so that we can apply another rule, and the theorem that we are going to introduce is theorem number 7, which has already been proved in the earlier module. P implies P or P. So look at step number 4 and number 5. Theorem number 5 is exactly the antecedent of step number 4. So by the application of the rule of detachment, we have in the step number 6, P implies P. Now we have just given a full-blown proof of theorem number 8. Now what I want to show is this, that by introducing a rule called derived rules or shortened form of rule, we can reduce the number of the step. That is, we don't need such a lengthy proof for this theorem. So let us look at how we can use these derived rules to shorten the length of a proof. We can straight away introduce axiom number 1, which is P or P implies P. That is step number 1. And the next step, step number 2, we can introduce theorem number 7, which is being already proved. That is, P implies P or P. And the derived rule says that if beta implies gamma and alpha implies beta, and if these two are proved or they are a thesis, then we can infer A or alpha implies gamma. And the same structure is here. P implies P or P, which is step number 2, and then P or P implies P. From here we can derive the next step, P implies P. So from step number 1 and 2 we have got the step 3, which is P implies P. We have seen that the length of the proof can be shortened by the application of derived rules, but we have not given a justification for these derived rules. The justification requires proof from outside the object language. So now we will give a meta proof for this derived rule which we have just used. Let us now take a look at the meta proof of this derived rule. So by showing that we can give a meta proof of this theorem or derived rules, we are also saying that these derived rules are redundant. So let us look at the meta proof. Now the proof which is given here is basically a kind of schema, a general structure. So there is a series of derivation coming which is indicated by ... and at a step M we have beta implies gamma, and then after a series of derivation we come to step number N, which says alpha implies beta. The next step we have is N plus 1, so which is therefore alpha implies gamma, which is the general structure of a derived rule. Now we have shown the general structure of a derived rules. We can generate a full proof, a meta proof for this general structure. And now let us look at this meta proof. This dot dot we see is an indication that there may be a series of derivation which has occurred earlier, and at a certain step m we have beta implies gamma, assuming that this is already a theorem, which means it has been proved or justified before. And dot 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 indicates that there can be a series of derivation, and at step n we have alpha implies beta. That means this has been derived from the steps above. And at step n plus 1 we have introduced theorem number 5, which says if Q implies R, then P implies Q together implies P implies R. So in this meta proof, what we will do is introduce structure and then provide right substitution. So these alpha beta are not part of the object language. These are in meta language. So we will convert them into the meta language now. So if we substitute every occurrence of P, which is in object language, theorem number 5, by alpha, and substitute Q by beta, and substitute R by gamma, we have this new structure. Beta implies gamma together implies, if alpha implies beta, then alpha implies gamma. Now this is in meta formula. At the step n plus 3, we will be applying one of the rules of detachment. So go back to step m, where we says beta implies gamma. That is the antecedent of the formula in n plus 1. So by the rule of this detachment modus ponens, we have in the next step n plus 3, if alpha implies beta, then alpha implies gamma, which is actually the consequent of the formula in n plus 2 step. We will again apply the detachment rule. Let us go up and look at step number n. So the step number n is already been proved. Now this step n is the antecedent of step number n plus 1. So if we apply the detachment, then we get the next step, which is alpha implies gamma. What we just did is that a meta proof can be given to those derived rules. So as mentioned, these derived rules are redundant. It is nothing new. The truths are already there, but in order to justify the use of this rule, we have given a meta proof. Just a small remark before we move on to the next point. That is, in the full-blown proof given in meta proof, we have introduced theorem number 5 as part of the derivation. Now actually we are not allowed to introduce this kind of theorem unless we provide a proof of that theorem. So assuming that theorem number 5 has already been proved, we are applying this theorem in this derivation, in this proof. Likewise, we can generate more derived rules from axioms or from some theorems. For instance, let us look at axiom number 2. The statement of the rule will be, if beta is a thesis, then alpha or beta is also a thesis. Or alternately, from the thesis B, one can derive A or B as a thesis. See, we have just seen that from axiom number 2 we can generate a derived rule called rule of addition. Likewise, if we remember theorem number 11, 13, from there we can derive rule of double negation. Or look at, if we can remember theorem number 6, from here we can have a derived rule of hypothetical syllogism. Now what we will see is we can also expand the language of axiomatic system. And how are we going to do that? That is by introducing equivalence. That certain equivalence by definition can be shown, and once the equivalence has been shown, we can use those equivalents to prove some thesis. Let us see how, for example, we can show equivalence involving conjunction. Alpha dot beta, that is alpha conjunction beta, is definitionally equivalent to negation of negation alpha or negation beta. Now this can be shown in a different way also, which is to say, when is alpha equivalent to beta? Alpha is equivalent to beta, that is definitionally, if alpha implies beta and beta implies alpha. In other words, alpha is materially equivalent to beta by definition if alpha implies beta and beta implies gamma. Now, given that definition, we can actually generate a number of theorems or derived rules. Let us look at some of those derived ones. Theorem conjunction 1. If P, then Q implies P and Q. Theorem conjunction number 2. If P, then Q implies Q and P. Theorem conjunction 3. If P and Q, then P. Theorem conjunction 4. If P and Q, then P. Theorem conjunction 5. If P and Q implies R, then P implies Q implies R. So we have seen how more theorems can be derived by showing the equivalence of conjunction. And once these theorems have been derived, we can now convert them into derived rules. Let us look at some of these derived rules. From theorem conjunction 1, we can have rule for conjunction. In fact, conjunction 1 and 2 give us rule for conjunction. And if you look at theorem conjunction 3 and also conjunction 4, we can have a derived rule, which is the rule for simplification. We have given a definition, logical equivalence of conjunction with some other thing, and then we have derived some theorem. And once those theorems are given, we can generate derived rules, and we have seen how conjunction help us to have this rule of conjunction and rule of simplification. Likewise, by introducing more equivalence, we can derive more theorems, and with the help of those theorems, we can have more derived rules. Let us look at implication or conditional. Theorem of equivalent 1. P implies Q is materially equivalent to if not Q implies not P. Theorem equivalence 2 is P materially equivalent to not P. Theorem equivalence 3. P materially equivalent to P and P. Theorem number 4. P materially equivalent to P or P. theorem equivalent 5, P and Q equivalent to Q and P. Theorem equivalent 6, P or Q equivalent to Q or P. Theorem equivalent 7, P and Q and R equivalent to P and Q and R. Theorem equivalent 8, P or Q or R equivalent to P or Q or R. So from these theorems which are generated by equivalence, we can now generate more derived rules. So let us look at those theorems and what are the derived rules that we can get from those theorems. From theorem equivalence 1, we have the rule of or rule for transposition. From theorem equivalent 2, we have what is normally called as rule of double negation. From theorem equivalent 3 and 4, we have rule for tautology. From theorem equivalent 5 and 6, we have a rule known as the rule for commutation. From theorem number 7 and theorem 8, we have rule of association. We have just seen how from definition of equivalence we can generate more theorems, and with the more theorems we can generate more derived rules. And the idea of equivalence is that when we have a formula alpha and then another formula beta, and if we can show the equivalence of these two, alpha and beta, then any occurrence of alpha in any complex formula can be replaced by beta. That is the idea. So let us look at some of the instance where we can apply the rule of substitution. Look here. From theorem conjunction 3, which is P and Q implies P, we can get Q and P implies P. On the basis of theorem equivalent 5, P and Q implies Q and P. In this case, P and Q in theorem conjunction 3 has been substituted, or you may say replaced by Q and P, as theorem equivalent 5 tells us that these two sentences are equivalent. These derived rules that we have just seen can be broadly termed as rule of substitution. So in the first case, we have seen rules of replacement, and now we have seen rule of substitution. That is generally put when we have a formula A and then it has subformulas B, and then if B is shown to be equivalent with another formula C, then in every occurrence of B we can put C and generate a new formula D. And if a complex formula A is a thesis, then the new formula that we have generated D is also a thesis. So we have just seen the rule of substitution, which is like substitution of equivalent formulas. Now, of course, a question or a doubt may arise: how is this rule different from the rule of uniform substitutions? Maybe we can give two. One, in uniform substitution, we have to uniformly substitute all occurrence of one by another, whereas in the case of this one, that is substitution of equivalence, we don't need to uniformly substitute. Wherever we want to substitute, if we can substitute in parts. The next difference is this, that in uniform substitution, we don't need to show that what is substituted and what is used to substitute need not be equivalent. We don't have to show this equivalence of these two. But in the case of substitution of equivalence, we need to show that these two are equivalent, and then we can use to substitute. That is the difference. Now that we have seen what are these rule of equivalent substitution, we can use this rule to derive some theorem. Let us look at some theorems. Let us have the theorem conjunction 3, which is P and Q implies P in our first step. And then we can have theorem equivalence 5, which is P and Q equivalent to Q and P. They are shown to be equivalent before. So given this step 1 and 2, we can arrive at the third step, which is Q and P implies P. Note that in the first step it is P and Q implies P, and in the third step the difference is Q and P implies P. How we are able to derive this one is because we have shown that P and Q is equivalent to Q and P. We have come to the end of our lesson, but before I wind up, let me quickly summarize the important points. Here we have shown that more rules can be generated once we have axioms and some rules, and then we can generate meta proof to justify those derived rules. Next, we have seen that more rules can be added, those rules of replacement. Here we are calling it as rule of equivalent substitution. Once we have these rules, then by showing equivalence of certain formulas, we can arrive at conclusion. So this brought us to the end of this module. Thank you.